So welcome back to our next video here at databasetutorials.com. This is object-oriented programming in C++. And in this video, we're going to be looking at continuing the basics of C++ and object-oriented programming. In our last video, we covered the basic program where we learned how to use cout to print text out on the screen, as well as using our include statements at the top there. So now we're going to continue on. It's going to continue to teach us a little bit more here on our basic program here and show us what it's like to use comments. Now, comments start with a double slash symbol and terminate at the end of the line. And this is one of the exceptions to the rule that the compiler ignores white space. A comment can start at the beginning of the line or on the same line following a program statement. Both possibilities are shown in the comments example. When to use comments, comments are almost always a good thing. Most programmers don't use enough of them. If you're tempted to leave out comments, remember that not everyone is as smart as you. They may need more explanation than you do about what your program is doing. Also, you may not be as smart next month when you've forgotten key details of your program's operation as you are today. Use comments to explain to the person looking at the listing what you're trying to do. The details are in the program statements themselves, so the comment should concentrate on the big picture, clarifying your reasons for using a certain statement or group of statement. So if we look at our comments here in Visual Studio, up here at the top we have console application 1.cpp. This defines the entry point for the console application. That's our first comment, and it's explaining what our console application is going to do. Next comment we have down here is this is a potentially very long comment. This is just an example that we have here, just to show that this is how you write a comment. You open up a single slash symbol and you put a star in between it, like this here. We could do a star here, and then you can put a comment in here, and then this will be multi-line, as you'll learn here pretty soon. And then as we just read about, there's going to be a double slash where if you write a comment in here, then it'll only be single line, and anything you put below it or on top of it won't be commented out. But if it ends up in the same line, then it will be commented out. Whereas the multi-line here can have plenty of white space in here, and you can put comments in multiple lines here. So alternative comment syntax. There's a second comment style available in C++. This is an old style comment, which we just talked about with the single slash and the star here. This type of comment, the only comment originally available in C, begins with the single slash star character and ends with the star slash, not with the end of the line. These symbols are harder to type since slash is lowercase while star is uppercase, and take up more space on the line, so this style is not generally used in C++. However, it has advantages in special situations. You can write a multi-line comment with only two comment symbols, as you can see here. This is a potentially very long multi-line comment. This is a potentially very long multi-line comment, as you can see here. So, this is a good approach to make a comment out of a large text passage, since it weighs inserting the double slash symbol every line. You can also insert a single slash star and single slash star single slash comment anywhere within the text of a program line. For example, if you open up your function one, you can put the comments in there. So if we were to be here in our int main, and there's your main function here, we could even come in here and we can comment in here as well. And it can be multi-line or it can be single line. If you attempt to use the double slash style comment in this case, the closing brace won't be visible to the compiler since double slash style comment runs to the end of the line and won't code compile correctly. Integer variables are the most fundamental part of any language. A variable has a symbolic name and can be given at a variety of values. Variables are located in particular places in the computer's memory, and when a variable is given a value, that value is actually placed in the memory space assigned to the variable. Most popular languages use the same variable use the same general variable types such as integers, floating point numbers, and characters. So you are probably already familiar with the ideas behind them. Integer variables represent integer numbers like 1 to 30,000 to negative 27. Such numbers are used for counting discrete numbers of objects like 11 pencils or 99 bottles of beer on the wall. Unlike floating point numbers, integers have no fractional part. You can express the idea of 4 using integers, but not 4 and 1/2. So, defining integer variables. Integer variables exist in several sizes, but the most commonly used is the type integer, as we can see here in our int main function. The amount of memory occupied by the integer types is system dependent. On a 32-bit system such as Windows, an integer occupies 4 bytes, which is 32 bits of memory. This allows an integer to hold numbers in a range of negative 2,147,483,648 to 2,147,486,647. I probably said that all bad, but you get the point. You're reading along with me. Now, figure 2.3 shows an integer variable in memory. While type integer occupies 4 bytes on current Windows computers, it occupied only 2 bytes in MS-DOS and earlier versions of Windows. The ranges occupied by the various types are listed in the header files limits. You can also look them up using your compiler's help system. So, here's a program that defines and uses several variable types of integer. So if we look at our bottom here, we see here at the top, let's say we want to open up another file here, and it'll just be another CPP file. And we'll just go ahead and at the top, we'll do integer variables.cpp. That'll be the name of this file. And then we're going to say this demonstrates integer variables. We're using our comments that we just learned about. And then we're going to do an include. It's going to include the IOStream, which we learned about that in our last video. If you don't know what this is, go back to our last video. And then we're going to say using namespace std, so we don't have to use stt later on in our call. And then we're going to open up an integer main function. This is going to be our main. And then in here, we're going to start off with our first integer variable. It's going to be int variable1. And then this is going to be our define for variable1. I'm just going to put comment next to it so you can know what it is. We're going to say int variable2. And then this is going to define our variable2. And if we continue to scroll down, now we see some mathematical calculations happening here. So now we can say, hey, variable1, let's set that equal to 20. And then let's set variable2 equal to variable1 plus 10. So what's that going to do? That's going to take variable1, it's going to plug it in here and then say variable1 plus 10, which is going to take 20 and do 20 plus 10. And then it's going to set this value equal to variable2. So now if we want to print it out on the screen, let's say cout variable1 plus 10 is, and then we can do our output text here. And then we'll actually print it out on the screen. We'll say cout, and then we'll say variable2. And then we're going to end line. That's what end L is. That's going to be our end line here. So this is going to be the output value of variable2. And then our integer main has to have a return 0 if it's not going to return any value there. So if we were to build this, build this here, then it's going to error out. And if we were to build and run this, then it's going to error out, and we need to put this in our CPP1 here. So let's just bring this over. Let's just bring this over here. And we just need to make sure we have this here, so that way we can use this. And I'll go ahead and I'll build it, and then we're gonna see if we can start it. There shouldn't be any build errors. Did you forget to add in your source? Let's get rid of this. Source.ppp, let's just remove that. And then let's just build that again. And let's just start that up. And now we can see here, variable 1 plus 10 is 30. And that's what it printed out on the screen. And actually, you guys can't see that yet. So let me just go ahead and let me just share that. And now you can see it. So variable 1 plus 10 is 30. That's what we just did here when we did a C out of variable 1 plus 10 is, and then we did a C out of the variable 2 there on the same line, and then we did an end line. So that's what that did. And then if we press any key to continue, then it'll just go ahead and it'll close out for us. So let's take a look at our next figure here. So this type of program, so if we type this program into our compiler's editor screen or load it from the website and link it and then run it, examine the output window, the statements int variable 1 and int variable 2. Define two variables, variable 1 and variable 2. The keyword int signals the type of variable. These statements, which are called declarations, must terminate with a semicolon like other program statements. Like we see here, we have semicolons being added at the end here. Now in highlight, you must declare a variable before using it. However, you can place variable declarations anywhere in a program. It is not necessary to declare variables before the first execution statement, as was necessary in C. However, it's probably more readable if commonly used variables are located at the beginning of the program. So for best practices, basically what that's saying is when you're creating a function or a program, you should create your variables at the beginning because it's most commonly used, and you must declare a variable before using it. So here, as you can see, before we were able to assign 20 to variable 1, we had to initialize that variable by saying integer variable 1, and now it's defining it. And the same was for variable 2, and then we were able to use both variables here to assign values to them after initializing them, and then we could use them in the cout statement here to print it out on the screen. Declarations and definitions. Let's digress for a moment to note a subtle distinction between the terms definition and declaration as applied to variables. A declaration introduces a variable name such as variable 1 into a program and specifies its type such as int. However, if a declaration also sets aside memory for the variable, it is also called a definition. The statements int variable 1 and int variable 2 in the int variables program are definitions as well as declarations because they set aside memory for variable 1 and variable 2. We'll be concerned mostly with declarations that are also definitions, but later on we'll see various kinds of declarations that are not definitions. Variable names. The program int_var uses variable name, variable 1 and variable 2. The names given to variables and the other program features are called identifiers. What are the rules for writing identifiers? You can use upper and lowercase letters and the digits from 1 to 9. You can also use the underscore. The first character must be a letter or underscore. Identifiers can be as long as you like, but most compilers only recognize the first few hundred characters. The compiler distinguishes between upper and lowercase letters, so variable is not the same as variable or variable. You can't use C++ keyword as a variable name. A keyword is predefined with a word's special meaning. Int, class, if, and while are examples of keywords. A complete list of keywords can be found in Appendix B, C++ precedence table and keywords, and in your compiler's documentation. Many C++ programmers follow the convention of using all lowercase letters for variable names. Other programmers use a mixture of upper and lowercase, as an int variable or data count. Still, others make liberal use of underscores. Whichever approach you use, it's good to be consistent throughout the program. Names in all uppercase are sometimes reserved for constants. See discussion on constants that follow the same conventions apply to naming other program elements such as classes and functions. A variable's name should make clear to anyone reading the listing of a variable's purpose and how it is used. Thus, boiler temperature is better than something cryptic like BT or T. So, when using variables, it's best practice to use a name that's going to be very easy to understand. A lot of programmers sometimes use underscores, so if we wanted to have our variable, we could have did this int variable underscore one, and then this would have been underscore variable one, and then we would have done a cout on variable two here. But you could also do variable one, like variable v1. You could have uppercase letters in there like that, and it would be the same thing as well. And the variable's name, I'll say that again, the variable's name should be clear to anyone reading the listing, the variable's purpose, and how it is used. Now, assignment statements. The statements variable 1 equals 20 and variable 2 equals variable 1 plus 10 assign values to the two variables. The equal sign, as you might guess, causes the value on the right to be assigned to the value on the left. So the equal sign causes the value on the right to be assigned to the value on the left. The equal sign in C++ is equivalent to the colon equal sign in Pascal, or the equal sign in BASIC. In the first line shown here, variable 1, which previously had no value, is given a value of 20. Integer constants. The number 20 is an integer constant. Constants don't change during the course of the program. An integer constant consists of numerical digits. There must be no decimal point in integer constant, and it must lie within the range of integers. In the second program line shown here, the plus sign adds the value of variable 1 and 10, in which 10 is another constant. The result of this addition is then assigned to variable 2. So, variable 1 equals 20. This is automatically an integer constant because it's not going to change during the course of the program. We've hard-coded variable 1 to be equal to 20, and that's not going to be able to change. Same thing goes here for assigning variable 2 equal to variable 1 plus 10. This is a constant because we've added 10 here, and this is not going to change throughout the rest of the program. Output variations, as we can see here, cout variable 1 plus 10 displays a string constant as we've seen before. When we do a build and run, this is going to be a string that shows in the console. And then cout variable 2 and an end line, as we see here. Displays the value of the variable 2. As you can see in your console output window, the output program of the program is variable 1 plus 10 is 30. If we were to build and run this again, we'd be able to see that, as you can see here. So, note that cout and the operator know how to treat an integer and a string differently. If we send them a string, they print it as text. If we send them an integer, they print it as a number. This may seem obvious, but it is another example of operator overloading, a key feature of C++. C programmers will remember that such functions as printf need to be told not only the variable to be displayed, but the type of variable as well, which makes the syntax far less intuitive. As you can see, the output of the two cout statements appear on the same line on the output screen. No line feed is inserted automatically. If you want to start on a new line, you must insert a line feed yourself. We've seen how to do this with the N escape sequence. Now we'll see another way using something called a manipulator. The N line manipulator. The last cout statement in our int_vars program ends with an unfamiliar word, N line. This causes a line feed to be inserted into the stream, as you can see here, N line, so that subsequent text is displayed on the next line. It has the same effect as sending the /n character, but is somewhat clearer. It's an example of a manipulator. Manipulators are instructions to the output stream that modify the output in various ways. We'll see more of them as we go along. Strictly speaking, nline, unlike n, also causes the output buffer to be flushed, but this happens invisibly for some for so for the most purposes the two are equivalent. So unless an end line is included after a C out, or unless something like a new line is added here, then it's going to automatically result in being on the same line. As we can see here, when we build and run this, it's going to be on the same line. So this end line made it so that way, let's say we wanted to do another C out here, and then we wanted to say, hey, give me variable 1, and then also give me variable 2. And then let me just go ahead and end line again. And then if I were to build and run this, you see now we have another line here, which is 50. So what it did was it took variable 1 and it added it to variable 2, which is 20 plus 30, which equals 50. So other integer types. There are several numerical integer types besides the type int. The two most common types are long and short. Strictly speaking, the type character is an integer type as well, but we'll cover it separately in a different topic. We noted that the size of type int is system dependent. In contrast, types long and short have fixed sizes no matter what system is used. Type long always occupies 4 bytes, which is the same as type int on 32-bit systems. Thus, it has the same range from negative 2,147,483,648 to 2,147,483,647. I probably said that wrong again. It can also be written as long integer. This means the same as long. There's little point in using type long on 32-bit systems since it is the same as int. However, if your program may need to run on a 16-bit system, such as MS-DOS or an older version of Windows, specifying type long will guarantee 4-bit integer types. In 16-bit systems, type int has the same range as type short. On all systems, type short occupies 2 bytes, giving it a range of negative 32,768 to 32,767. There's probably not much point using type short on modern Windows systems unless it's important to save memory. Type int, although twice as large, is accessed faster than type short. If you want to create a constant of type long, use the letter L following the numerical value, as in long var equals 7678L. Assigns long constant to 7678 to long var. Many compilers offer integer types that explicitly specify the number of bits used. Remember, there are 8 bits to a byte, and these types names are preceded by 2 underscores. There are underscore int8, underscore int16, and underscore int32. Int64, the underscore int8 type, corresponds to character, and at least in 32-bit systems, the type name underscore int16 corresponds to short, and underscore int32 corresponds to both int and long. The underscore int64 type holds huge integers with up to 19 decimal digits. Using these type names has the advantage that the number of bytes used for a variable is not implementation dependent. However, this is not usually an issue, and these types are seldomly used. So, we're not going to go too deep into this one. This video is probably already peaking 20 minutes. And so far what we've learned was how to create multi-comments. We've learned how to create single comments. We also learned how to create variables. And then we've learned how to define those variables and to declare those variables as well, and to assign values to those variables. And then we also learned how to take that variable data and print it out on the screen and to build it and run it and show it in our console. So if you're interested in our next video, you know what to do. Head on over to database-tutorials.com and check it out. Also, subscribe to our YouTube channel. And yeah, until next time.